I'm not sure all of you understand just how groundbreaking and innovative this technology is. There is a lot of innovation here that you just cannot see. And you look at the extent of collaboration between all of these companies, it's absolutely amazing. And that's why we're thrilled to have these companies come and present. So I know I have 1,000 questions for them myself, but I will open it up to the floor if anyone else has questions. Microphone.
Okay, I'm Jose Rivera. I'm with the Control System Integrators Association. Just quick question. Why Wyoming?
Wyoming is the largest energy exporting state in the United States. They produce a tremendous amount of coal, and they have a tremendous amount of oil and gas resource. A lot of that's been under attack, and the state is extremely supportive of keeping its coal industry in place. And our plant will both consume coal in a zero emissions manner, but then give them a diluent for enhanced oil recovery. So they're then also net able to produce oil. And so due to those factors where we present a significant economic upside for the state. Further, the governor and the different politicians have been wanting an alum fet cycle plant running on coal for the past 5 years, and we're now working to develop that. We also wanted a brownfield site, which Pacific Corp had. Pacific Corp ran analysis across all post-combustion technologies and ours, and ultimately decided that ours was the more economic case. And so we have a supportive host and partner where we can use existing permits, and then we have a very supportive government for the technology. But we also see North Dakota as being an opportunity, as well as some of the other locations that I indicated.
Thank you.
Yeah.
Next question. All right. Well, let me put one in here for Peter. Peter, I think I know we discussed this a little bit earlier today, but this technology can burn all kinds of fuels, right? It can burn coal, it can burn biomass, it could be natural gas. But some of those fuels have a lot of kind of pollutants in them. How do you deal with the sulfur in coal, or the NOx and SOx emissions, or any of these other emissions? Is this technology, where do all those pollutants end up going, and how is this technology able to deal with that?
Thanks, Rick. The constituents like the sulfurs on the AFCC would be coal, as Damien explained, for the feedstock. We have a lot of experience there, including operating the world's largest gasification plant in Saudi Arabia. And so from the sulfur separation, that would be covered on the gasification side. There's some things there that we're further looking at to offset some of the parasitic loads relative to the ASU, and that's taking some of the waste heat off the gasifier. So we're looking there at all of the other areas we can drive energy as part of these processes, specifically the gasification. You would have a similar process for the biome when it comes to the overall wood feedstocks going into that. I think one matter of interest on that is we foresee there's going to be basically recipes for each end operator. And so part of that, we're developing now a specialized combustion test center where we can basically take the recipe, if you will, either on reuse of other waste streams, so cellulosic materials, coal, for instance, whether you're looking at Powder River Basin, lignites, if you start looking over in areas such as South Asia, China, respectively, Indonesia, vast difference in blending and mixtures for solid fuels. So for that, what I foresee is we're going to have a number of recipes that are going to be suited for each client. And for that, we would need to tune the individual combustors. And so the combustor, just like that with a gas turbine, will basically be tuned for a range of fuel constituents going into it. We're quite confident that we can basically custom tune each of the fuel blends going into this. Respect to natural gas, yes, all of our base testing will be done on natural gas. I think if we look at the full spectrum of fuels, from one end, looking at mixtures such as recycling of waste streams, perhaps the most complicated going into that, even on the gasification and on the secondary side. If we look on the other extreme, where there's basically a very homogeneous on natural gas, that for us is viewed as the simplest. And of course, the objective is there to find the most robust system. We're talking now the combustors that can fire that entire blend across the API range for what that customer needs.
Just to add, on the back end of the gasifier, we're looking at Selexol, which is typical in the industry to purify syngas in chemical production. So that's what we would use to get a clean syngas. And the system does not generate any SOx or NOx because we fully control what goes into that combustor. It's not an air-breathing machine, so you don't have nitrogen that converts into NOx, and we can control the sulfur. So the only place that nitrogen or sulfur enter the system is through the combustor. If you do have ppm level of either one of those, it's designed to knock it out in the water tower. So they come out in the water tower. So you can place this thing in, non-attainment zones. There's no particulate, no SOx, no NOx, no emissions from the facility. We've also cleared this with the EPA that this only requires a minor source permit.
Well, that's very. I made the rookie mistake earlier today asking them, what do you deal with NOx? Oh, we don't have to worry about NOx. We don't have any nitrogen coming in. We just have oxygen. Oh, it was, should have been obvious, but I didn't think of it at the time I asked it. So now I have a background as a light commissioner. We follow the utility industry. We see that the utility industry is struggling to deal with the non-dispatchable solar and wind and batteries. We know that ISO New England, RTOs, ISOs all over the country are putting together plans and creating markets that will pay a premium price for those suppliers of electricity that can deliver it for peak demand, for handling our peak units, for handling crises. I guess a question here for Damien is, I think I didn't quite completely understand everything you talked about in terms of the ability of this technology to ramp up quickly, to be able to reduce generation if there's a lot of renewables on the grid, and then to be able to put all of that power, to put a maximum amount of power when you're really required to in the peak load times like 5 to 7 p.m., for example.
Yeah, so the peaking capability has to do with the fact that we have the parasitic load from the air separation unit. The air separation unit will consume 64 megawatts of parasitic load when the plant is running full tilt. That'll allow the plant to put 250 megawatts to the grid. If you have dewars, oxygen storage tanks, you can store oxygen when you turn your plant down because you're not fully consuming the oxygen. Then when you want to peak the plant, you can produce, instead of 250 megawatt electric, 280 megawatt electric to the grid. So you can peak 30 megawatts instantaneously by just pulling oxygen from the tank instead of putting full load to the air separation unit. This is what we call molecular energy storage, which is a different kind of energy storage, which has no capacity fade, is extremely cheap. We can put in 3, 4, 10, 25 days of storage. We've run studies with Air Liquide, GE, and SWERI to assess what is the economic viability of this oxygen storage when you put an AFC in different grid systems with varying degrees of renewable penetration. And we can fully support a grid system with 50, 60, 70% renewable penetration and ensure that there's consistent energy supply to all the consumers in the region using the oxygen storage mechanism from the power plant. As far as turn down, there's a good amount of thermal inertia in the plant, and there's a decent amount of parasitic load, right? We do have the compressors and pump, but we can very quickly go to net zero to the grid, but we're still running the turbine. We don't have to stop the turbine. It can keep running because we want to keep the plant warm, and we have plenty of parasitic load around the plant that can absorb that electricity, you see. So that's part of the flexibility characteristic of the plant.
So with a warm plant, you can come back up to full load quickly.
Yeah,
Yeah.
the hardest, I mean, the technology, I think, will ultimately be a paradigm shift for how the world produces electricity, full stop. The problem is that everybody just wants to use the absorbers that they're familiar with, even though they're thermodynamically nonsensical, right? They do it because it's familiar, right? And that's human nature. But we just need to, and it takes a while. So we've been, he was talking about the Valley of Death, and I couldn't help but think about, I've wandered through that valley for a number of years.
I think something I would also point out is carbon management in general offers a lot of opportunities to build flexibility into our systems. I think a lot of people are very worried that, if I apply a carbon capture technology, I'm going to limit the system that I have. No, if you do the right planning on the front end and you build in some things like storage, whether that's in a system like Damien described, or whether that's even in a simple solvent system, you can do load shifting, you can do triaging and things like that, and you can end up providing kind of grid services that could be really, really valuable at a much cheaper cost than some of the other options out there today, or whether that be a peaking unit of some sort or even some energy storage technologies as well. So that's something we as industry and utilities need to work together on is, all right, if you do this, I can do that, and we can all achieve this because of it at that point.
And I think the other important point on the post-combustion that's important is these AFC plants are new build, so they don't address existing plants. And
Yeah,
so that's where post-combustion makes
It's
a
more,
ton of sense.
I would think of it, I've been sitting through a lot of these talks on automation and controls this week, and I'm a chemical engineer who's worked in the process, like the actual operations side of carbon capture during my career, so it's a little bit different for me. But to steal some terms I've heard, this is more of a rip and replace. Like if you have an opportunity to do something new, this is a way that may be more efficient. If you need to make some incremental steps, post-combustion capture can be a way to use what you've already got and still achieve the change you're looking for at that point.
And in fact, we're actually, the three of us, are the three organizations, we are working on post-combustion together as well. We've got a system called KC8, which is aqueous potassium hydroxide post-combustion carbon capture system, which should be coming online in May at NCCC. Eight Rivers is a prime on a DOE grant, and Siemens Energy is developing the control system for that. So, because AFC is a new build, I did recognize the gap that we don't have anything to offer to existing fleet. And we'll get that data, and then hopefully KC8 will be on your slide soon enough.
Yeah, we look forward to that being on the list there, Monica.
Yes.
I think one other, just from the standpoint of the operational flexibility, I think you've got a couple of unique perspectives there. One, looking at the potential, say, for post-combustion capture on existing assets. And that's something we're looking very closely at respect to protecting the fleet as far as service and over the entire life of the existing asset, how we can give customers a pathway to capture. In the case of AFC, yes, it is a so-called new build, but what we're finding also is that there's a significant amount of an existing generating site that can be complemented. And I think one other thing is when you look at the overall numbers respect to the CapEx, I would urge you to look not just at the cost of electricity. And I know for me as an electrical engineer, that's something I often struggle with, levelized cost of electricity. But you're one, essentially replacing an entire new asset as far as that entire powertrain. And so you're basically providing now an entire new life to that existing, say, site in the case of the Wyoming project. The other part of that is to look at that full spectrum of what are the constituents that you're modernizing. And it's easy to look at just CO2 incentives nowadays, oh, that's to sequester. But if you look at off-tank of, say, the argon, the modernization of the site, and in cases of what I call the friendly 8 states, there are a number of states in the U.S. that value EOR, value CO2 in their own state as an important commodity that they don't just want to bury and sequester, but to utilize, say, in stimulation of their oil and gas industries that are indigenous.
Another question from the audience? Anyone? So, ARC, we've covered electrolysis, all right? And if you have electrolysis, you know, you're putting electricity in and you're making oxygen and hydrogen. This process describes, well, it got its oxygen by distilling air, all right? It's got pure oxygen from distilling air. But many of the electrolysis processes, the oxygen is waste product and it's vented in the atmosphere, and that's the feedstock for this material. Aren't there other ways that you can combine the production of hydrogen and with this operation and seems like that has a good working possibility?
Like I know from Siemens Energy view, we're trying to play in as many of the fields as well as conventional as possible. I know, Rick, you had mentioned with both the green and the blue hydrogen and potential SMR as those come online and nuclear. So we're participating in all of those currently. And yes, as a byproduct to an existing thermal process, that's part of the creativity, looking at what you can take off of that for production of hydrogen. Inversely, for say the process for AFC, O2 or artificial air is one of our key ingredients going into that. So one could say, looking at refineries, areas where there's already a green hydrogen site, say adjoining a wind field, you could have a very nice coexistence with something that's basically vented, which is the O2, and start now to have a codependent relationship with that adjacent partner for completing the chain and utilizing things. And I think that's one of the areas to really look at how to maximize all of, not only offtake of others, but what the end deliverables are at these sites.
Yeah, it seems like the possibilities for collaboration. And when he said SMR, that was not necessarily a steam methane reformer. That was a small modular reactor
Right.
that was making hydrogen. We got to be, so now we have another situation where you could collaborate with nuclear power.
Just some metrics for everybody. If we were to take oxygen from electrolyzers, which are currently all venting their oxygen, we can lower the OPEX 20 to 30%. And the OPEX is the primary driver in the levelized cost of hydrogen. The problem is that nobody has been monetizing the oxygen stream, and that oxygen-oxygen double bond in the molecule has stored renewable energy if it's on a green basis. And we're venting a ton of that energy, where we could take it into this system. So if you had a 30 megawatt electrolyzer, we would need 37 of those 30 megawatt electrolyzers running at a 92% capacity factor in order to supply the AFC. If you wanted to ramp those electrolyzers up and down, you simply add oxygen buffer storage, and now you have consistent supply of oxygen. You can produce hydrogen. I can lower the cost of hydrogen by 20 to 30% by giving a revenue stream for the oxygen offtake. That then allows me to build a smaller ASU. So I save CapEx, and the counterparty gets a new revenue stream. There are very few situations in this energy transition where people are focused on where's the economic win on both sides of the fence. But we've found these efficiencies, and Siemens has the sialyzer, and the sialyzers that are sold are venting their oxygen. I've been wanting to follow Siemens around to those customers and get options contracts on that oxygen for the next 20 years. Just say, listen, I'll pay you $500,000 for the next 10 years. You, no matter what, are going to sell me $20 ton oxygen, and I can come in and get that whenever I want it. These kinds of arrangements, I think we'll start to see this pop up in the 2030 timeframe after we've delivered the first unit. And from a turbine perspective, the other interesting thing, and this is a point I made to the Siemens Energy Board at one point, was that these AFC turbines are actually hydrogen turbines. Hydrogen is just not pure. We've got carbon monoxide there, and we've got CO2, but that's syngas. This is a hydrogen burning turbine. Yeah? And that becomes really compelling that you're combining hydrogen burning from the syngas with CO2 capture.
I think in several of the presentations we had earlier in this week, there was a lot of comments and emphasis on the necessity for collaboration. And I know, John, your organization, the National Carbon Capture Center, I mean, you have put together, you've collected so many different types of companies. It seems to me, are you kind of like a vector to help interconnect the EPCs to the turbine makers, to the technology makers, to the chemistry guys,
Yeah, that's one of the things we try to do is make sure we have the technologies connected with the eventual end users, to make sure we're getting them connected with the right kinds of people to partner with down the line. I make a point, people often say, well, what's your favorite technology that you've seen coming through the National Carbon Capture? And I'm like, well, it's not that easy. Maybe it'll be KCA, we'll see. But it's more than just what's the base performance of the technology. It's also, what is the rest of the team going to look like that they're going to put together to deliver that technology when it actually comes along down the line. And that's kind of a benefit that Southern Company gets and our sponsors get through kind of seeing things up close through participation in the project, is they get to see what the strengths and weaknesses beyond just the core tech are. Oh, well, this group, maybe you really are going to have some questions about who's their EPC partner, because that's not something they have in-house. Or, right. Oh, maybe this one, they have some strengths there. This is the weakness we have with them instead. That's the kind of thing that we're trying to identify and then provide our connections and experience to those technology developers so they can address all those problems as quickly as possible.
Yeah, great. All right, well, we're coming to a close. I do have to say that, my favorites tend to be those that have thermodynamic wins, and there's some definitely very favorable thermodynamics in this particular process. And so in any event, I'm going to just close with that, and I thank you very much, and give us a hand for our speakers.